The universe is a prominent place, and we're just exploring it. As technology improves and more powerful telescopes are coming online, the famous James Webb is only one of them, we'll be able to see farther into space than ever before. The nearest stars are fascinating because they have been studied for so long that their properties are well known. You could say they're our cosmic neighbors. Let us take a quick glimpse of some of them. Proxima Centauri. The nearest star to our solar system is Proxima Centauri. It's a red dwarf, which means it's not massive enough to fuse hydrogen in its core, like our Sun does, and has a lifespan of approximately 10 trillion years. The distance between Proxima Centauri and Earth is about 1.3 light-years away. In other words, we would need to travel at the speed of light for over 4 years before reaching this star. A red dwarf like Proxima Centauri emits far less light than our Sun, so much so that it would appear as little more than a faint speck of light even if you are standing right next to it. Proxima Centauri also has another feature that makes it unique from most other stars in our galaxy: its flare activity. This means that occasionally there can be violent outbursts on or near the Sun's surface. The most oversized flares have been observed producing flares 100 times more intense than those made by our own Sun. Wolf 359. Wolf 359 is the most distant of all the stars we can see with our naked eyes without a telescope. It's about 7.8 light-years away, which means that if you're looking at it right now, and you are, you're also looking at what was happening in our solar system 7.8 years ago. The closest star to Earth after the Sun is Proxima Centauri, at 4.2 light-years away. That means that if we traveled at 1/100th of the speed of light, it would take us 4 hours to get there. Wolf 359 has been thoughtfully nicknamed Buffy because its surface temperature is too hot for life like ours. Around 2,300 degrees Kelvin, 4,700 degrees Fahrenheit, Buffy's mass and luminosity are like those of our Sun, so much so that scientists even suspect it might be part of an identical twin. It also has an age closer to ours than other red dwarfs, about 3 billion years old versus 12 billion for Proxima Centauri and 40 billion for Barnard's star, another nearby red dwarf not far from Buffy in terms of distance, but further away along its orbit around Sol. Lalande 21185. Lalande 21185 is a red dwarf star about 8.5 light-years from Earth. It's like our Sun, but it has a planet called Lalande 21185b. This planet is about the same size as Earth and orbits its host star in just over 9 days. Epsilon Eridani. Another star that is reasonably close to Earth after the Sun is Epsilon Eridani. It's a binary system. One of the stars in this system is slightly larger than our Sun, while the other is smaller. That makes it a yellow dwarf. It has a surface temperature of 5,500 degrees Celsius, more than 10 times hotter than our own star, but it's cooler than other stars such as red dwarfs. Epsilon Eridani could be only 10.5 light-years away from Earth, which means that if you were to travel there at light speed, which we currently can't do, it would take only 10.5 years to get there. Its planet, HD 21749b, may have water on its surface and even life forms. 61 Cygni A. We have many reasons to be interested in this solar system. First, it's one of the closest, if not the closest star system to Earth we've discovered so far. Also, it contains 2 stars that orbit each other every 42 years, like our own Sun and its companion planets. The first star system discovered to have a planet is 61 Cygni A, a binary star system about 12 light-years from Earth. The primary star is 61 Cygni AA, while its companion star is 61 Cygni AB. The two are red dwarfs, low-mass stars that are cooler than our Sun, but still emit enough energy for life as we know it on some planets orbiting them, such as Earth. Tau Ceti. Tau Ceti is a star that is 11.9 light-years from Earth. It's a G-type star and a yellow dwarf, which means it has roughly the same surface temperature as the Sun. The habitable zone of the Tau Ceti system sits between 0.8 to 1.4 AU astronomical units from its central star, which is equivalent to about 0.6 to 1 billion kilometers, or about 600 to 1,000 times closer than our current orbit around the Sun. Barnard's Star. Barnard's Star is the fourth closest star system to Earth. It is located 5 light-years, 3.1 parsecs away, towards the constellation of Ophiuchus. It has an apparent magnitude of 9.5, making it visible to the naked eye in dark skies. The star has a mass only 0.14 times that of our Sun, and a radius half as large, resulting in a luminosity 10% smaller than our Sun. Its metallicity is like that of Sol's. An abundance index near naught would suggest almost no metals or all metals, with iron being the most abundant metal, while an abundance index near 1 indicates all elements are present. Its effective temperature is 8,130 degrees Kelvin, with surface temperatures ranging from 7,730 to 8,570 Kelvin. The age of this red dwarf is estimated to be around 6 billion years. Groombridge 34 AB. Groombridge 34 AB is a binary system of two stars separated by only about 1.5 astronomical units, or about 1/7 the distance from the Sun to Mercury. The primary star, the larger of the two, is similar in mass, size, and luminosity to our Sun, while its smaller companion is around 1/3 as massive and emits only about 0.4% of its light output. This makes it a red dwarf star like Proxima Centauri, the nearest known star system to Earth. But Groombridge 34 AB's red dwarf isn't quite as close as Proxima Centauri. In fact, this stellar pair would be considered part of Alpha Centauri if there weren't already 3 other stars in between them. UV Ceti. UV Ceti is a red dwarf star. Red dwarfs are small, long-lived stars that emit less radiation than other types of stars like yellow or blue supergiants. Red dwarfs can be up to 10 billion years old, but they don't become main sequence stars until they reach the age of 2 billion years. That's because they burn at lower temperatures than more prominent stars, which means that they are fainter in visible light and have a longer lifespan before reaching the end of their lives as white or black dwarfs. UV Ceti is an active flare star that regularly emits high-energy particles into space in bursts lasting from seconds to minutes. These flares are thought to be caused by magnetic fields interacting with the stellar wind, a stream of charged particles flowing out from its surface. UV Ceti also varies significantly over periods ranging from hours up through weeks. These variations happen because it has a strong magnetic field that causes intense flares and pulsations depending on where its poles face Earth at any given moment. There is a lot of cool stuff in our solar neighborhood. To learn more about these systems and the planets that orbit them, we must first understand how astronomers classify stars. We will find more exciting discoveries as we expand our reach and explore the unknown. However, as I have said before, it is essential not to forget about our cosmic neighbors in this process. While many of them may seem insignificant on the surface, or even too far away for us to ever consider visiting them ourselves, and maybe they are, there is still so much exciting stuff going on in our immediate neighborhood that we should keep an eye on. There are millions of stars in the universe, from tiny red dwarfs to majestic blue giants. Some stars twinkle for billions of years, while others burn up almost instantly by space standards. Our journey today takes us to some of the most exciting places. Our home planet gets further away from us with each new star we discover. Our closest star will be the starting point of this journey of thousands of light years. Together with the Parker probe, the Sun will brush its scorching corona and peer into its fiery depths. Once we've checked out some exoplanets closest to Earth, we'll leave our home system and travel farther to Alpha Centauri. Afterward, we're up for a long journey of several hundred light years to meet a shiny Altair, a tremendous Fomalhaut, and mysterious Arcturus. We will ultimately reach Betelgeuse, a dying star, and a CW lens, a giant red lens. Our final stop will be a unique space object with extremely high temperatures. 9,500 light-years from the Earth, a scorching massive star awaits anyone with the bravery to approach it. Known as WR102, as far as we know, it is the hottest star in the universe. A real-life inferno. Get ready and let's begin. The Parker Solar Probe was 8.5 million kilometers from the Sun on November 21, 2021. Our parent star's boiling outer layer. Our star was closest to it at that time. As well as brushing against the corona of the Sun, it was also the first probe to do so. Our system star has already been studied. Why was it necessary to overcome several technical difficulties and approach the Sun closely? The purpose could only be realized if it reached areas where everything around turns to ash. How does Parker fare after that? First, approximately 4.6 billion years have passed since the Sun formed. On balance, it belongs to spectral class G2V, which makes it a yellow dwarf. The Sun's surface temperature is about 5,800 degrees Kelvin, or 5,530 degrees Celsius. However, there are also hotter and colder areas on it. Additionally, the outer corona and inner layers of the star are scorching hot. The visible radiation is barely affected by them despite all that. The star has a mass of 2 × 10⁻30 kilograms, or 333,000 times that of Earth, accounting for 99.9% of the entire solar system. Around 1.4 million kilometers is the average diameter of the Sun, which is 109 times the size of our planet. Despite our perception, the Sun is more prominent and brighter than 80% of all the stars in our galaxy. There is 92% hydrogen in the Sun's overall volume. A star's core gradually accumulates helium after hydrogen nuclei release tremendous energy. As stars merge, their temperatures reach extremely high values, fueling thermonuclear reactions which fuel their evolution. Currently, helium makes up 7% of the Sun's volume and 25% of its mass. Other elements in the stellar matter include carbon, oxygen, nitrogen, and iron. Their percentage, however, is relatively small. There are several layers in the Sun, each with different properties. The star has a massive core at its center. Approximately 25% of the Sun's overall size is measured by its diameter. Temperatures in the core reach 14 million Kelvin, while 1 cubic meter weighs about 150 tons. Every second, thermonuclear reaction, the source of our star's luminosity, runs here. These processes convert approximately 4.26 million tons of stellar matter into luminosity. The radiation zone surrounds the core, which is 0.7 times the radius of the Sun. Heat is carried to the star's upper layers due to this area's high density of matter. As a result, energy is transferred here because photons are continuously absorbed and re-radiated by the stellar plasma particles. This part of the star's temperature dramatically changes from 7 million Kelvin at its depth to 2 million Kelvin at its exterior. Approximately 10,000 to 170,000 years may pass before the quantum of light produced by the core moves to the next layer. The convection zone forms the outermost layer of the Sun and is relatively dense. In the convection zone, rarefied and changeable stellar matter creates enormous vortices. Plasma masses from the outer areas of the layer are slightly cooled as they move down these vortices, bringing hot plasma from deeper regions of the coating to the surface, as it were. A convection cell remains stable for 10 to 15 minutes, then is destroyed to give rise to a new vortex. A magnetic field is created as matter moves continuously in the inner solar system. An atmosphere surrounds the Sun as well. The structure consists of several layers. The photosphere is the lowest one. Most of the star's visible light comes from this area. It can be observed from Earth during a total solar eclipse or by using special equipment. This photosphere is what we see when we watch the Sun. A temperature fluctuating between 6,330 and 4,130 degrees Celsius is associated with a thickness of 100 to 400 kilometers. The chromosphere is around 2,000 kilometers thick and is found higher up. The temperature in this area is sweltering. A temperature fluctuates between 4,000 Kelvin and 20,000 Kelvin. The corona is the uppermost area of the Sun's atmosphere. 1 million kilometer-sized prominence, flare and emission may be found there. Incredibly, its outer border is covered with continuously active jets of hot gas, reaching a staggering 5,000 to 10,000 kilometers in height. The coronal matter is extraordinarily rarefied and hot, with an average temperature of 1 to 2 million Kelvin and a peak temperature of 20 million Kelvin. The chromosphere and corona can only reach such mind-boggling temperatures with the energy released by the photosphere. As a result, the upper layers of the Sun are heated up by some unknown physical phenomena. In this area, the Parker probe occasionally travels, immersing more deeply and profoundly into the blazing abyss every time. This thermal paradox has been explained by several scientific hypotheses. According to one of them, magnetic shock waves disperse energy into the chromosphere and corona. In another explanation, charged particles are accelerated by the star's magnetic field. To study obscure processes in the upper layers of the Sun's atmosphere, the Parker Solar Probe was specifically designed to investigate these phenomena. NASA launched the Parker Solar Probe in 2009 as part of a project known as the Parker Solar Probe. On August 12, 2018, 9 years have passed since August 12, 2009. To fulfill its mission, Parker took off from the surface of our planet on a one-way trip to the Sun. It had to use Venus's gravity to execute several maneuvers to achieve the desired orbit. The scorching, blazing ball in the center of our solar system slowly drew closer to Parker as he adjusted his trajectory. Despite the searing heat of the star, it was ready to withstand it. All equipment was designed for extreme conditions, including the heat shield on the probe. Parker's orbit should also be close to the Sun for a relatively short period before pulling back and giving off heat. As a result, thermal exposure is alleviated. The probe's primary objective is to describe the structure and dynamics of the magnetic fields near the Sun. The probe's scientific instruments are photocameras, particle capture devices, magnetometers, and radiation detectors. As well as measuring the flow of energy emitted by the Sun, Parker is supposed to register waves in its corona and capture particles of stellar wind. During the probe's drift towards our parent star, it took photos of Venus and comet Neowise as a side mission. This mission is influenced by several factors. Ionizing radiation also threatens the measuring instruments in addition to critical temperatures. Data collected by the probe cannot be transmitted to Earth easily due to the Sun's substantial interference in the microwave range. Despite this, the Parker probe continues to accomplish its mission with every turn of its orbit. As the star gets closer, the distance between us decreases. By 2024, a new portion of data will be collected by passing through the Sun's corona in late February 2022. We will be able to reach the surface of our star in just 6.5 million kilometers, an all-time short distance. According to estimates, the probe's solar shield may reach 1,370 degrees Celsius at perihelion, 3 times hotter than Mercury's sunny side and slightly lower than Ion's melting point. It travels 163 kilometers per second at its perihelion, but will eventually accelerate to 200 kilometers per second, making it the fastest manufactured space object. It will have a short life expectancy when it reaches the closest point to the Sun. About a year will pass before Parker completes several orbits around the planet. As the ship loses speed, the scientific instruments on board will be exposed to extreme temperatures and powerful radiation. All of them will eventually malfunction, and the probe will sink into a fathomless ocean of blazing plasma to be totally swallowed up by it. We will be able to take yet another step forward in space exploration as Parker beams valuable data back to Earth. Around 100 years ago, the Earth began emitting structured radio signals into space. It took years for radio noise from the Earth to reach dozens of other stellar systems, including Arcturus, 37 light-years away, and Aldebaran, 65 light-years away. Additionally, our radio signals might be detected on the surfaces of many potentially habitable exoplanets, such as Ross 128b and Gliese 667cc. In this way, Parker's flight wouldn't have been in vain. Alpha Centauri remains the nearest triple star system to the Sun, making it the ideal destination for the first interstellar flight. The stellar system Alpha Centauri consists of 3 components. You can see 2 larger ones relatively close together with the naked eye. There appears to be only one source of light. It takes around 80 years for the 2 components to complete their orbit around the common mass center. There is a maximum distance between the stars of 35 astronomical units and a minimum length of 11.2. Alpha Centauri A is the most massive, brightest, and most prominent star in the system. Its mass is approximately 108% that of the Sun. Alpha Centauri A's radius is 1.22 times that of our Sun, despite its surface temperature and spectral class being like that of our star. There is a 1.5-fold increase in energy output. The distance between these objects and the Sun is 4.36 light-years. Neither this star nor its environs have been confirmed to host exoplanets. However, the infrared observations of the star in 2021 revealed evidence of a nearby planet-like object. Its mass may range from 9 to 35 Earth masses, and its radius may measure 3.3 to 7 times that of our planet, which is 1.1 astronomical units away from its parent star. Approximately a year passes before the hypothetical celestial body completes a full orbit around it. Alpha Centauri b, or Talisman, is the second component of the system, and it also belongs to the main sequence. Despite this, it has a mass of 10% less than the Sun, and its radius is only 86% of the Sun's, Our star is also slightly more relaxed than Solomon. Observations with the James Webb Telescope or Earth-based observatories are needed to verify the data. Temperatures on its surface are estimated to be 5,260 degrees Kelvin, slightly below 5,000 degrees Celsius. Combined with these factors, the celestial object has an orange hue and a luminosity twice as low as the Sun's. Interestingly, Alpha Centauri b emits more X-ray energy than other objects in its class. As well as its temper, the star exhibits bright flares and ejections. Neither this star nor its surrounding region has been confirmed to host exoplanets. It was suggested in 2012 by astronomers from the Geneva Observatory that there might be a planet very close to Earth with an orbital period of 12 days and a radius of slightly less than Earth's. Observations of the star's proper motion over the past 4 years led to the suggestion. However, data processing discovered a mathematical error 3 years later. Hence, the idea that there is a planet was incorrect. A stark contrast exists between the first two components of the system. An approximate 12% of the mass of the Sun makes it a red dwarf. Compared to the Sun, its size is about 7 times smaller. A meager 0.17% of the star's luminosity can be attributed to its surface temperature, which is slightly higher than 3,000 degrees Kelvin. It lies 4.25 astronomical units away from the Sun, making it the closest component of the Alpha Centauri system. Proxima Centauri means closest relative in Latin. Compared to its two stellar companions, Proxima is noticeably distant. Furthermore, the object is getting closer and closer. As a result, it will be only a bit more than 3 light-years away in 26,700 years. Due to its low luminosity, this star cannot be seen from Earth. In terms of light-years, this distance is approximately 13,000 astronomical units. Solar System Planet 1. The orbit around Proxima's common mass center takes 547,000 years. Proxima Centauri boasts 2 confirmed exoplanets and at least 1 hypothetical planet. Several small celestial objects, such as asteroids and comets, may also be present around the star, including a dust ring. A radial velocity method was used to detect Proxima Centauri b in 2016. The discovery was confirmed in 2020 by a spectrograph study with the largest Earth-based telescope, a gigantic telescope called VLT. According to the updates, the exoplanet orbits its parent star every 11 Earth days and lies 0.05 astronomical units away. Its mass is estimated to be 10 to 20% greater than Earth's, and its radius is 1.3 times as large. Mathematical modeling determined that Proxima Centauri b receives about 1.5 times less thermal energy from its star than Earth. As the celestial body is exceptionally close to its host star, it could theoretically have liquid water in some areas, as its temperature is 234 degrees Kelvin or 39 degrees Celsius below zero. Due to its tidal lock, it faces the star on the same side as another. Such conditions require a dense atmosphere to compensate for sharp contrasts and temperatures. However, Proxima Centauri is also observed to eject stellar matter like other red dwarfs. There are also flares of ionizing radiation observed. The gradual destruction of the atmosphere of the closest objects is believed to be the result of such activity. Even if Proxima Centauri b has a strong magnetic field, it is unlikely to provide much protection against destructive forces. By 2020, the existence of another planet in the system has been confirmed. Near the center of the solar system is a space object called Proxima Centauri c. It orbits the Sun once every 5 years. There is no estimate of the object's radius, but its mass is probably 6 to 8 times Earth's. As Proxima Centauri c lies a considerable distance from its parent star, the exoplanet will fall either into mini-Neptunes or super-Earths, depending on its size. There are 234 degrees Celsius below zero in its temperature, or 39 degrees Kelvin. According to some observations, a ring system on the planet may have a radius 5 times that of Jupiter. The exoplanet is also expected to lie between 0 and 9 astronomical units away from its parent star, which has a mass of about 25% of the Sun's. It remains unclear whether this space object is accurate, and further confirmation is needed. A year on this planet could last about 5 Earth days, and its surface temperature could be 360 degrees Kelvin or 87 degrees Celsius if it exists. Alpha Centauri has been listening to our radio signals for over 100 years, but we can't cover the 40 million kilometers of space vacuum between us at this point. Such speeds are still unfathomable for humans, taking light over 4 years to gather. Even today's fastest state-of-the-art spacecraft would need tens of thousands of years to cover this distance. Travel time could theoretically be significantly reduced by utilizing advanced technologies. There have been many proposals for spacecraft that would have been capable of navigating interstellar distances since the dawn of space exploration. However, none of them have been designed. One of these missions is still under active consideration, but most have been forgotten. In the first half of this century, up to 1,000 microprobes could be sent to Proxima Centauri as part of the Breakthrough Starshot program. A centimeter is a maximum size they will reach. Unique, thin and durable land sails will be blown out by impulses from an Earth-based laser to assist the probes. It is estimated that an interstellar investigation will leave the solar system at about 20% the speed of light, with a travel time of about 20 years. Data collected by the mission will reach Earth in about 5 years. Within 50 light-years of the solar system, there are approximately 1,400 stellar systems. The number of our celestial neighbors exceeds 2,000, since some of them contain multiple objects. The stars range from dim red dwarfs to dazzling giants whose temperatures are beyond our comprehension. In all their diversity, space objects are astounding in scale and abundance. It's a waste of time to keep track of them all. Shortly, we'll be traveling at incredible speeds, much faster than the speed of light. The trip will take a few minutes to cover dozens of light-years. Our journey around the solar system will take us to several remarkable objects in space. The stars and worlds of the future are already waiting for us. A detour of 11 light-years would have passed in the blink of an eye after we flew around Proxima Centauri, wherein the dim red dwarf known as Ross 128 could be found. As far as we can tell, we cannot see it from the Earth. Unprepossessingly, however, Ross 128b appears to be orbiting this star like Earth. We are one of the closest exoplanets to it. Unlike Proxima Centauri, which is more immediate and cooler, assuming its surface is identical to that of our planet, which absorbs 70% of light that falls on it, Ross 128b has a moderate temperature ranging from -60 to 21 degrees Celsius. Ross 128b has an equilibrium temperature of around 7 degrees Celsius. Although it is 8 degrees cooler than today's Earth, it is still warm enough to support life. There is a 35% difference in mass between the Earth and the exoplanet. At this point, the planet's radius has not been accurately measured, but its composition likely is the same as Earth's. Its diameter is about 10% larger than Earth's. Its freefall acceleration is only 12% greater than our planet's. the conditions on Ross 128b's surface should be comparable to those on Earth if all these estimates are accurate. In addition, the system is racing towards the Sun. We will be closer to it in 79,000 years than Proxima Centauri, which is moving away from us. Concerning its host star, Ross 128, exoplanets like this are standard. There is quite a distance between Ross 128b and its host star. The distance between it and the system center is only 0.05 astronomical units, or 20 times shorter than between the Earth and the Sun. The exoplanet completes a full orbit around its star in less than 10 days. Additionally, it is believed to be tidally locked. Approximately 17% of the Sun's mass, with a radius almost equal to that of the Sun, at 3,192 degrees Kelvin, its surface temperature is twice as low as that of the Sun, as is its luminosity. Ross 128 has a relatively constant and regular luminosity as a comparatively quiet star. Rarely does it flare up or emit stellar matter. This is so pernicious to all living things. Traveling 12 light-years away from the Sun in a direction pointing away from us, we will be able to see the light in the star, also known as GJ273. It has one of the largest planetary systems detected among the closest planetary systems to Earth. Despite its orange hue, the star is only 25% as massive as the Sun. High-precision measurements of the star's proper motion led to the detection of the first confirmed exoplanet. Compared with the Sun, its radius is 3 times smaller, and its luminosity is 435 times lower. As a result, it is only visible through a telescope. A total of 4 objects have been detected in their surroundings, 2 of which are confirmed exoplanets. 2 others are still prospective candidates awaiting confirmation. The object is estimated to weigh about 2.89 times the mass of Earth. Compared to our planet, its radius is 35% larger. As a result, the object may be considered a super-Earth, and its surface gravity may be suitable for humans. There are roughly 0.1 astronomical units between the system center and light and B. Even though the amount of light received by the exoplanet from its parent star is comparable to that received by us from the Sun, thus, light and B are in their star's habitable zone and could be considered potential candidates for alien life searches. Earth's equilibrium surface temperature is between -14 and 19 degrees Celsius, or 259 to 292 degrees Kelvin. As a result, human beings can quickly adapt to light conditions. A second confirmed exoplanet is Light and C. The mass of this space object is like that of the Earth, but it lies much closer to its host star. The orbital parameters of the object have not yet been determined, but it completes a full rotation around its system's center in just 4.7 days. The celestial body is likely to be scorching hot and harsh, with no atmosphere, always facing the star. Preliminary estimates indicate that the 2 other objects in the system were discovered in 2019. The orbit radii of their ice giants lie within 0.8 astronomical units, with masses from 5 to 15 times those of Earth. There can be no more than 558 days in their orbital period. These 2 objects lie outside the habitable zones of Lyton, a relatively cold star with shallow temperatures. These 2 candidates still require further exploration at this point. It goes without saying. We will come across a star named Altair, 16.8 light-years away from the Earth as we move away from the Lyton system. The star is bright and wide. It has a mass of approximately 1.8, It has an estimated age of 1.2 billion years. It is one of the most conspicuous stars in the night sky because its luminosity is 11 times that of the Sun. In addition to Altair's fast rotation, it has another curious characteristic. As a result, the Earth spins on its axis approximately 67 times faster than the Sun. The star's shape is far from an ideal sphere due to its rapid rotation. In slightly less than 9 hours, it completes an entire course. Approximately 286 kilometers per second is the speed of star material at the equator. The star's equatorial diameter is rough, twice the diameter of the Sun, and 22% larger than its distance between its poles. Different areas of the star have different temperatures and luminosities. It is noticeable that stellar matter at the equator is cooler and darker than at the star's poles. At the equator, the temperature is just 6,900 degrees Kelvin. Alternatively, the bars can reach temperatures of 8,500 degrees Kelvin, approximately 8,200 degrees Celsius. The irregular shape of Altair was determined by theoretical calculations. A disk-like profile was finally confirmed in 2007 when an image of the star was produced. Altair became the first star outside the solar system to have its surface imaged. There have been no planets detected around Altair. Yet, as light is dispersed in these structures, a fog or rings envelop the star Altair, causing a curious effect. The significant interference of light around the star creates a vast rainbow. Despite its beauty, it does not conceal the star and significantly impedes its study. For a long time, this stellar system has consisted of 3 components. Previously, it was considered to be a mutually independent space object made up of 3 parts. It was found in 2013 that they are gravitationally bound, forming a large and single structure in space. There are probably fewer multiple star systems close to our solar system than Thermal Haud. After carrying through the area for 25 light-years, we will reach Thermal Out. Its components are separated by 3.2 light-years at their most significant distance. Between the distant objects in the Thermal Haud system, nearly 11 lunar disks may be visible in our night sky. Thermal is this system's most significant, well-known and well-seen component. It is a young, hot star with a mass 92% larger than the Sun and a radius 1.85 times the Sun's. The star Fomalhaut has been called Fomalhaut since ancient times, unaware that there are other components not so easily observable in this system. The star is remarkably bright, with a luminosity 16 times higher than the Sun. Approximately 8,500 degrees Kelvin or 8,200 degrees Celsius is its estimated temperature. Today's stellar evolution models estimate the age of Thermal Haud at 400 to 480 million years. There is a possibility that the star will grow to be around 1 billion years old. When it reaches this age, it will probably turn into a white dwarf and go supernova. There are several segments of protoplanetary gas and dust surrounding Fomalhaut A. With a diameter of about 25 astronomical units, its inner radius measures 133 astronomical units. Celestial bodies are regularly born on this disk, which is an active stellar nursery. Astronomers are therefore keenly interested in it. There was once a belief that Fomalhaut was home to a massive planet. Dagon was even given the name. The observations, however, revealed hardly any planets. Exoplanets are usually assumed to be vast clouds of dust. At 0.9 light-years away from the system's main component, it would have formed from the collision of asteroids and comets. W Pisces, also known as Stringy, lies on Fomalhaut b. It is an orange dwarf with a mass of approximately 70% that of the Sun and a radius of roughly 63% of the Sun's. The star's surface temperature is about 4,700 degrees Kelvin, which is 4,400 degrees Celsius. It is interesting to note that the star's luminosity is much lower than that of the Sun. There is a 5-fold difference in brightness between our host star and our star. As of 2019, analyzing proper motion and spectral data, according to scientists, celestial bodies orbiting a star may weigh between 8.6 and 1.9 Jupiter masses. Currently, the exact parameters of its orbit aren't known, but the existence of this body remains a mystery. According to preliminary estimates, the hypothetical planet should take 25 years to complete a full orbit around its star. LPI 876-10 completes a full rotation around Fomalhaut in approximately 20 million years. The Fomalhaut system's third star is LP 876-10. Its surface temperature is slightly over 3,100 degrees Kelvin, and the star is 5 times lighter than the Sun. There are 2.5 light-years between the red dwarf and the system's main component. According to the system's birth, the red dwarf would have orbited its big brother just 22 times. No planets or exoplanet candidates have been detected near the star so far. Yet, observations suggest a cloud of dust and gas surrounding it. What is a star's radius with a diameter of 10 and 40 astronomical units? Currently, we are 37.3 light-years away from the Earth. This is the distance we would have traveled to reach Arcturus, the Northern Hemisphere's fourth brightest star in the night sky. A binary star system consists of a star as its main component. There is a giant orange planet whose life is coming to an end. Having transformed most of its hydrogen into helium, the star is now burning the remaining stellar fuel and gradually expanding. Its surface temperature is 4,251 degrees Kelvin, but it emits 170 times more luminous energy than the Sun. A tremendous stellar stream named after Arcturus has also been named after its brightest star. Approximately 2 billion years ago, the Milky Way absorbed a dwarf galaxy that produced this massive structure. A total of 53 stars are present in it. Most of them are old, dim, and not nearly as impressive as Arcturus. Because its mass is just 10% larger, it used to be like our Sun. What will be the inevitable result of the depletion of its stellar fuel and the internal pressure of its scorching hot plasma? A 25 times larger orange giant evolved from the star. Following today's theory of stellar evolution, in the distant future, our Sun will undergo this process. From 6 to 8 billion years is considered the age of Arcturus. In astronomical terms, it will go supernova relatively soon at the end of its life cycle. As Arcturus sheds its outer layers, it will become a scorching hot white dwarf that will eventually cool down. Against the background of its giant companion, the second component is barely visible. As it lies close to Arcturus, this small star, with a luminosity 20 times lower than that of Arcturus, is impossible to define. It is likely that even if some planets could form millions of years ago, they were absorbed by Arcturus. The star's surroundings have not been detected by either method. Betelgeuse's luminosity is reported to have dropped suddenly by astronomical observatories. Within 2 months, its luminosity decreased by 36% by the end of 2019. A supernova is expected to be the brightest object in the night sky. This explosion produces gamma rays that are potentially dangerous for life on Earth. By April 2020, Betelgeuse's luminosity has recovered to the expected level, according to astronomers. There is no way to predict when it will go supernova, but it may happen at any moment. The most popular hypothesis is used to explain anomalous fading. Very recently, on June 2021, Betelgeuse ejected a giant cloud of gas and dust in the direction of the Sun. Betelgeuse is something you should be aware of. Earth-based telescope data confirm the assumption. Astrophysicists model its interior, while astronomers observe the object before figuring out what is happening. Red supergiants like this object are at the end of their life cycles. Theoretically, the outer layers of a star are highly unstable, and their luminosity and radius are constantly changing. Millions of scorching gas are regularly emitted into space, forming gargantuan prominences as they cool. Gas nebulae surround Betelgeuse due to their presence. It has a mass approximately 17 times that of the Sun, and a diameter of roughly 700 to 880 times that of the Sun. The planets up to Mars and most of the asteroid belt would be swallowed up by Betelgeuse if placed in our system's center. Due to its fragile outer layers, the star has no clearly defined edge. A gargantuan gas nebula containing cooled-off prominences, protuberances, and stellar wind particles encircles the object. The star's conventional boundaries have a higher astral matter density than the nebulas. The star Betelgeuse is remarkably bright. There is 90,000 times more luminosity in this star than in the Sun, and 150,000 times more in this star than in the Sun. It is interesting to note that the temperature of the star ranges from 3,400 to 3,800 degrees Kelvin, which corresponds to the red spectral band. It is difficult to predict the processes in the star's outer layers since they are unstable. It is possible for them to elaborately change the luminosity of an object. There are fewer distinct cycles with more extended and smaller periods than the main pulsation period of the star, which is around 420 days. In addition, occasionally the star can experience unpredictable flares and dimming. Calculating the distance between us is complicated because this star is so unstable. Based on current concepts of stellar evolution, the distance between the Sun and Betelgeuse is between 500 and 650 light-years, according to the Coriolis satellite in 2020. In its original mass, Betelgeuse would have exceeded 20 solar masses. It formed around 8.5 million years ago. Gravity forces would have been gradually compressed and heated up from a giant cloud of interstellar gas. In its interior, the temperature and pressure reached a level where hydrogen reacted with helium to create helium gas. Hence, Betelgeuse was born from the protostar. It is the first stage of the main sequence. After moments of thermonuclear interaction, a new star appeared in the night sky. Whenever a star begins its most extended life, this is how it begins. Their primary energy source is the merger of hydrogen atoms and nuclei that produces helium. As helium accumulates in the object's center, it forms a helium core. There is no doubt that heavier stars run this process faster. A massive star like Betelgeuse can live for only a few million years, whereas a red dwarf can live for billions. Regardless of its life cycle, a star passes through the main sequence for over 90% of its lifetime. It almost entirely depends on what happens next to the mass of this star. At the end of their existence, stars with masses less than 20% of the Sun did not go supernova. Their hydrogen eventually runs out, unlike more massive stars, and they slowly turn into blue dwarfs, hot and comparatively small objects. It is doubtful that any blue dwarf will be discovered today, since it takes around 1 trillion years to complete this transformation, 72 times the assumed age of the universe. After hydrogen is exhausted, thermonuclear reactions will cease, and the star will become a tepid black dwarf, barely visible through telescopes after 1 trillion years of slowly fading and cooling. An object's evolution goes through more elaborate processes if its mass lies between 0.2 and 8 solar groups. Stars expand, their radius grows, and their outer layers cool. Due to thermonuclear reactions, helium contributes to the core of the star, while gravity forces compress and heat it up. As helium nuclei merge, carbon is produced. In this case, a red giant or a supergiant forms. Yellow stars whose masses are less than 50% of the Sun cannot sustain the conditions necessary for helium and carbon chain reactions. In such objects, transformations like these are pretty irregular. Reactions occur with heavier objects. The star's core may produce carbon, oxygen, and heavier elements like Nico and Ione as it runs for more extended periods. After the outer layers of the star are shed, what is left is a white dwarf enshrouded in a planetary nebula. Without a greater mass, the original star would be mainly composed of helium with just a small amount of heavier elements. White dwarfs, on the other hand, would be principally composed of carbon and oxygen if the star was more severe. Massive objects evolve according to specific laws. It is estimated that the more serious a star is, its core will be enormous, with a mass 8 times or more than the Sun. Since the original star was heavy enough, it will contain neon, magnesium, and iron. According to Chandrasekhar, its core may have a mass 1.4 times that of the Sun. Due to gravitational compression, internal electromagnetic repulsion is not strong enough to compensate. As the core shrinks, the outer layers pool in its wake. Electrons are literally crammed into atoms' nuclei by extreme compression. Many neutrinos are produced due to the electrons being converted to neutrons. Even a material as dense as that can't hold back the universe's most elusive particle in a few seconds. Some thermal energy is taken with neutrinos as they escape the collapsing star. As a result, the tightly packed protons repel each other with great force, causing solid internal pressure. Due to this, the core expands as rapidly as it shrank a few seconds earlier. As a result, the surrounding material is subjected to tremendous shock waves. The star's outer layers can be thrown enormous distances by a tremendously powerful explosion. This is where the star has been. Reactions that are impossible elsewhere can be unleashed by its flames. As a result, heavy elements such as gold, lead, and uranium are produced. Byproducts such as the nebula gradually cool and disperse into different clouds, which are later compressed by gravity and become stars and planets. Neutron stars are tiny but weighty objects. On explosion, if the original star's mass was 18 to 20 times that of the Sun, its core is expected to shrink to form a black hole, which distorts space and time. Modeling shows that massive stars with masses more than 100 times the Sun's mass could theoretically be obliterated by the blast. The shock wave will scatter the material they are made up of for many years or transform it into potent electromagnetic radiation. Several hundred light-years can be covered by a supernova's electromagnetic impulse. First, the radiation is concentrated, annihilating all living things on its path. Lethal rays gradually disperse into space as the distance grows, reducing the density of the flow. This star is unlikely to go supernova in the next 100,000 years, but it will likely do so soon. It is estimated that a star like Betelgeuse could threaten anything within 100 light-years. According to estimates, Betelgeuse may flare up as bright as the full moon. By then, the neutron star will no longer be visible to the naked eye, and the radiation it emits will only be visible with very powerful telescopes. The dying star will dominate our night sky for a while and gradually fade away. Betelgeuse may leave behind a black hole if it goes supernova with a greater mass than currently assumed. A minor energy flare will result in a less impressive sight in this scenario. Earth is not in danger either way. We won't be affected by a gamma-ray flare accompanying Betelgeuse's supernova because it lies too far from our solar system. We will not see the material ejected by the explosion for 6 million years. Before reaching the inner regions of the system, its speed is estimated to be around 13 kilometers per second. A distance of 650 light-years from the Earth, it could reach a radius of 560 times the Sun at its peak of pulsation, or about 2.6 times the distance between Earth and our parent star. The IRS plus 10 to 16 is located there. CW Lioness is also known as a majestic star lioness. All planets up to Mars would find themselves under CW Leonis' surface, which would even brush the inner border of the asteroid belt if positioned in the middle of our solar system. It's worth noting that the star has a relatively small mass, between 1.5 and 4 solar groups. About 2000 degrees Celsius is its surface temperature, which is just 2300 degrees Kelvin. As a result of its impressive dimensions, the star emits, on average, 8,500 times more energy than our Sun. CW Leonis is like any other red giant in its final phase of life. Several billion years are estimated as its age, but it is not precisely defined. Based on what we know about CW Leonis, it is assumed that it was a white-blue star with a mass 3 to 5 times that of the Sun. By 1 billion years ago, however, most of the hydrogen in celestial bodies had burned out and been converted into helium. Hydrogen was ejected by the helium, resulting in a scorching hot core without thermonuclear reactions. The star slowly settles into its center. Red giants are formed when a star undergoes this process, typical of stars near the Sun in mass. The inner pressure of the star causes the outer layers to become rarefied and unstable due to the expansion. A blood-red hue gradually takes over the object's color as its diameter increases dozens of times. Despite its depths, the stellar plasma still undergoes a thermonuclear reaction, increasing its pressure and temperature. As a result, helium nuclei become carbon at a certain point in the chain reaction. The helium flash is referred to as such. In a structure, it is a complex, multi-level physical process in which the core heats the outer layers, changing the stars dramatically to darken and cool off instead. Currently, there is a large amount of carbon in CW Leonis, but its mass is not sufficient for nucleosynthesis to proceed. The object's interior becomes unstable because of thermonuclear combustion. Gravitational forces gradually cool and shrink stellar matter. A new power is unleashed when the star interior heats up again. In this foam, the stars are enveloped in a gas nebula composed of carbon and oxygen. Stellar matter partially detaches from the star during contraction. Once the astral matter receives an unused amount of thermal energy, it expands again and the combustion ceases. It is believed that this cyclic process is responsible for the occasional changes in the brightness of the star. At its brightest, CW Leonis is 11,300 times brighter than the Sun, with the lowest luminosity having a 649-day pulsation cycle. Compared to the Sun, the object emits 6,250 times more energy. Circumstellar Nebula is about 1.5 times as large as the Sun and is 69,000 years old. It is 84,000 astronomical units in size. The nebula has an elaborate structure with bulges and pockets of gas, half-arcs and irregular rings. Based on the chemical composition of the cloud, it is posited that these formations appeared because of magnetic activity and stellar wind generated by the unstable star. Approximately 7 times the mass of the Earth, CW Leonis loses 4 times 10 to the power of 22 tons of material every year because of this process. Explorers are very interested in the shroud enclosed by the CW Leonis. Based on spectral analysis data, it contains around 70 different chemical compounds, including carbon dioxide, water, and ammonia. Mendeleev's periodic table also includes elements from the upper part down to iron. There may have been planets on CW Leonis in the past, but they were swallowed up during the expansion stage. Regardless, years of observations have revealed no evidence of their past existence. The star's orbit was observed to change subtly in 1994, and mysterious shifts of matter were detected in its gas and dust cloud in 2017. Observations of its radiation have been unsuccessful, but some small red dwarf orbiting the giant might explain these phenomena. A nearby light source may disperse and reflect the energy from the nebula. As a result, objects in the immediate surroundings become camouflaged and cannot be accurately identified. CW Leonis's hypothetical stellar companion should be significantly smaller than the Sun, and it should take approximately 100 years to complete a full orbit around the giant. Additionally, the star's environs and envelope contain much water. Initially, it was thought that the star would melt and swallow icy comets as it expanded. In 2009, however, observations showed that some spectral lines reached 1000 degrees Kelvin, which is only possible in the giant's upper layers where water vapor forms. At the time, the model of the red giant structure assumed all oxygen was still needed for water synthesis and must be used up ultimately in carbon monoxide production. As an explanation for the observed phenomena, you proposed that silicon oxides and carbon molecules are destroyed by powerful ultraviolet radiation. A scorching hot water vapor results from the reaction between oxygen released and hydrogen. Its weakness is that it does not account for the source of ultraviolet radiation. Temperatures above a certain point may induce reactions like that. In stellar matter, that is the case. Cosmic rays cannot penetrate it, however. There is yet another assumption that may explain this paradox. Large ruptures and low-density areas occasionally occur on the surface of the star due to its instability, where ultraviolet radiation is not entirely blocked out. There are several quintillion tons of water vapor in the star's atmosphere, which makes up the bulk of the atmosphere. The figure is enormous despite its appearance. According to today's theories of stellar evolution, water makes up just around 1/1000th of the star's overall mass. As a red giant, CW Leonis is now in its autumn years. After a powerful explosion, it will discard its outer layers after it depletes its stellar fuel in the next 10 to 30,000 years. As it transforms into an incredibly dense and hot space object, it will become highly thick and hot. It is a white dwarf. A few seconds after the transformation, its temperature will reach several million degrees, and its mass will be approximately 80% that of the Sun. Despite this, it will gradually and irrevocably fade away without an energy source for billions of years. When it becomes a mysterious black dwarf, the celestial body will appear almost invisible against the background of cosmic emptiness. There is no chance of this happening shortly. A global cataclysm or destruction is an inevitable part of the universe's evolution. During a shockwave and at the epicenter, elements like uranium, gold, and lead will be created that cannot be found in a star's interior. Millions of years from now, they will be incorporated into new celestial objects. The radioactive decay of the planet will, however, heat its interiors, melt its ice, and saturate its oceans with microelements, creating the conditions for life to emerge. Despite the storms, there are always rays of light at the end. There is a fiery inferno several thousand light-years away from the Sun. Near a small star, the surface is so scorching hot that any celestial bodies become ashes. Had barely retained its shape because it was burning so rapidly. A powerful flare will be produced when this object explodes. There are only a few such things we know about so far. A unique and dangerous situation, the hottest star in the universe is WR102, because this is the first spacecraft. Stars have extremely high interior temperatures. It is not surprising that thermonuclear synthesis, the primary energy source of all stars, is only possible under these extreme conditions. Hydrogen atoms merge to produce helium, several neutrinos, and an electron. Although hydrogen-helium synthesis is one of the processes that heat up stars at higher temperatures, it is not the only one. Other elements can participate in chemical reactions as well. Carbon or lithium, for example. Additionally, considerable energy is released during the process. Heavier parts such as sulfur, magnesium, and phosphorus form the cores in this case. As a result, their charge is higher and their repellence is more robust. Overcoming this resistance requires a great deal of energy. Main sequence stars begin to expand and cool when their hydrogen supply runs out. As a result, it gradually cools down. As it ages, it turns into a red giant. As helium transforms into carbon and oxygen in thermonuclear reactions, it will continue to burn. As a result, a lighter star will burn for a shorter period. As it becomes unstable, it sheds its outer layers and goes supernova. After depletion of all its energy sources, it becomes a white dwarf without any resources to fuel thermonuclear reactions. Even after all hydrogen in a star has been used up, heavy thermonuclear synthesis may become the star's primary energy source when its mass is higher than a specific value. Celestial objects such as these are known as Wolf-Rayet stars. French astronomers Charles Wolf and George Elliot discovered this class of space objects in 1867. The anomalously bright emission lines of heavy elements in these star spectra caught the scientists' attention. These unusual celestial objects were accounted for much later in terms of their inner makeup. These stars tend to be heavy. They are at the end of their revolution. Discovered in 1971, WR102 is now known as a celestial body. Initially, it was mistaken for the optical counterpart of GX3+1. Further observations, however, revealed that the two objects were completely different. As determined by spectral analysis, the discovered star had unusually bright oxygen lines in its radiation spectrum. Therefore, WR102 and 4 other bright stars formed the first class in 1982. Among the studied stars, the hottest belongs to the oxygen spectral sequence. Its surface temperature is over 210,000 kelvins based on spectral analysis. Our Sun is approximately 36 times as hot as WR102. This scorching hot object is unbelievably bright. It is estimated to be over 380,000 times as bright as the Sun. The distance between WR102 and Earth is approximately 10,000 light-years. It can be found in the constellation Sagittarius in the part of the sky where it is located. However, despite its high luminosity, it is too far away from us to be seen with the naked eye. The star WR102 is currently classified as an infrequent star. 9 such objects have been discovered, 4 in our Milky Way galaxy and 5 in other galaxies. The oxygen content of WO2 is exceptionally high, and the hydrogen content is shallow. It primarily relies on merging heavy carbon and oxygen cores as an energy source. Oxygen spectral sequence stars are rare for 2 reasons. To begin with, Wolf-Rayet stars are rare because only stars with a mass not less than 40 solar masses are potential candidates. The second characteristic of this class is that it represents the final stage of the evolution of stars of this type. From 1,000 to 10,000 years may pass, mere seconds in astronomical terms of comparatively modest size. Its radius measures just 58% that of the Sun, which makes it a dense star. During its birth, its mass is estimated to be between 15 and 18 solar masses. According to estimates, it weighed as much as 40 to 60 solar masses. Despite this, the star's high temperature and solid chemical reactions generate a mighty stellar wind with a particle velocity of over 5,000 kilometers per second. In a few months, it will lose enough material to equal the mass of Earth. This particle emission rate will result in the star losing 1 sun's mass worth of material in 10,000 years. No planets are orbiting WR102, but it is shrouded in a gas envelope, not dense, and exposed to powerful ultraviolet radiation and stellar winds. Around the star, the envelope contracts, maintaining its elaborate structure of protuberances and arches. The universe does not only have WR102 as an outstanding blistering place. WR102 may be surrounded by gas clouds that are remnants of its former hydrogen outer layer, according to one theory. Another theory maintains that the cloud formed due to the particle flow emitted by the star. The central sign, for example, is WR142, WR30A, and WR93b. As hot as 200,000 kelvins, the bug is in the constellation NGC 6302. White dwarfs may have similar surface temperatures. All of these, however, cannot compete with neutron stars. There is a possibility that neutron stars may reach temperatures of 100 billion Kelvin when they are born. The neutrinos cooled them off relatively quickly due to active neutrino emissions. Neutron stars always have a surface temperature of a few 100,000 kelvins, regardless of how they are formed. The reason for this must be that they are even hotter. Nevertheless, it is improbable that the ultimate temperature record will be broken. According to today's cosmological concepts, the hypothetical Big Bang had a temperature of approximately 1.4 times 10 to the power of 32 Kelvin. This is a fundamental physical constant. Planck temperature refers to this value. Contemporary physics cannot define a substance at a higher temperature because physical laws are distorted under such harsh conditions. Returning to WR102, compared to main sequence stars, this star appears to be in its autumn years based on our data on stellar evolution today. When a star reaches its final stage of life, it does not expand. As a result of their substantial mass, the chemical elements in WR102 are heavy and even iron is present. Later in its evolution, it will reach a critical point. As the star's life cycle draws to a close, a lot of proton and neutron capture will occur. By doing so, still heavier elements are formed, including transuranium. The neutron star will eventually replace WR102, a celestial body so dense and hot that it will be unbelievably hot. A nebula will slowly form as the outer layers of the former star are disrupted by the explosion. After billions of years, it will emit heat into the surrounding space. It will be possible to develop a new planetary system with this material. There are undoubtedly many beautiful and majestic stars, but what we have visited is just one of the most outstanding. Our galaxy is home to billions upon billions of other planets, many of which we are only beginning to discover. Stars are born and constantly die, contributing to the diversity of chemical elements in the universe. Planets wouldn't be able to exist without cosmic circulation, and without planets, no life would exist. Our view of the starry heavens is only possible because of faded stars from a long time ago.